Okay, welcome everyone. We'll get started so that Shannon can have the full time. It's my pleasure to introduce Dr. Shannon Curry here with us from Berkeley Space Sciences Lab today. Shannon has a bunch of fancy roles and titles, so I wrote them down. She's currently the principal investigator of the MAVEN mission at Mars. She's also project scientist for the ESCAPADE mission, an upcoming mission to Mars. She's the Deputy Assistant Director of Planetary Science at Berkeley's Space Sciences Lab. And Berkeley's where we overlapped when I was a postdoc there. Prior to Berkeley, she got her bachelor's from Tufts and a PhD from Michigan in 2013. One of my favorite things about Shannon is that she actually worked at Lockheed as a systems engineer before getting her PhD. And so for students who are interested in kind of different career paths and where you end up, Shannon's a great person to talk to. So Shannon's research is focused on terrestrial planetary atmospheres and particularly atmospheric escape. Today, instead of hearing about all the Mars work she's been doing, we're actually going to hear a bit about Venus and some results from Parker Solar Probe. And so Shannon, I'll give it to you. Thanks.
Thank you, Lauren. I know I usually have my Mars hat, but this is nice to actually get to come a little closer to the sun and talk about Venus. So the solar probe campaign didn't almost happen. Originally, Parker Solar Probe had no intention of turning any of their instruments on to observe Venus. And luckily, enough of us sat on the same floor, we just kind of had this uprising and marched into Stuart Bale's office and insisted that we just turn just a few things on. You wouldn't even know we were there. And so luckily, that's actually set the stage for things like the BepiColombo and the Solar Orbiter, Venus Flybys, which I'll talk a little bit more about too. So I want to start with why do we get so excited about Venus and Mars in the larger context of things? So at Mars, one of the biggest motivating factors has been following the water. So here you can see Earth, Venus, and Mars. And you can look at the time scales of volcanic activity and then the presence of liquid water. This is a figure from Darby Dyer from Nature. What's interesting here is that we really think hard about the presence of liquid water at Mars, but we really don't have the same kind of understanding at Venus. We just don't know what the presence of stable liquid water was like at that time. And this is a major piece of the puzzle for habitability. So one thing to point out too, one of the many reasons I get excited about atmospheric escape as a reminder is that liquid water to be in stable form needs to have enough atmospheric pressure, right? Or it's going to evaporate. And so when we think about Mars in particular, we know it had liquid water, and we think about where did all the atmosphere go? But the story's a little bit different at Venus. So it's not the same follow the water paradigm. So first let me talk, and also I should point out, you see all this volcanic activity here? That's a huge piece. So this is a figure from Dave Brain and some of his colleagues on atmospheric sources and sinks. Just to do a few things, outgassing via volcanic activity. There are a lot of different processes. I actually won't go into a lot of depth here, but the thing that I'm going to be focusing on today are going to be basically the thermal escape and things like photochemical, sputtering, and ion escape. Basically, these are the loss mechanisms from an atmosphere to space. And again, these really affect the dynamics of a planet. Okay, but let's again go back to thinking about all three at the same time. Okay, so here you'll look at the bottom. I put the surface pressure here because people always forget there's a huge, even though these planets formed at a similar time, and even though Mars and Venus have these CO2 atmospheres, they're really different planets. At Earth, we sort of normalize our surface pressure to 1 bar to ourselves. At Mars, we're looking at around 6 to 7 millibars. So again, most of that atmosphere has escaped to space. And at Venus, it's got 90 bars. So the question is not where did the atmosphere go, but where is it coming from? Because now we have different terms to think about. It's not just where did the atmosphere go, but if we know there's atmospheric loss occurring at Venus, there has to be something replenishing it to get up to 90 bars, as opposed to something like Mars. So then we can start to think this is where it can help thinking about atmospheric escape directly infers, or helps us understand things like volcanism and those outgassing and those replenishing, those sources of atmosphere. And so this is one of the links where we actually have the plasma physicists and the geologists who can get in the same room and actually have a fruitful conversation. So again, just as a reminder, Earth has a nice dipole magnetic field, right? So if you have a compass, it's going to point towards north. Mars and Venus are what we call weakly magnetized. At Venus, we don't think, or we have not observed, any kind of magnetic field, so we'll call it unmagnetized. And at Mars, we have these crustal fields. I don't know if you can see my mouse. No, you cannot. Here's the pointer. Well, at Mars, you can see those clearly highly scientific green little bubbles in the southern hemisphere, and those are the strong crustal fields. And so that's one of the big differences here. And Dave Breen's our resident expert, but magnetic fields, the jury's really out on whether magnetic fields can shield a planet from atmospheric escape, or in fact actually create more pathways for more escape. But that's an important distinction between the two. So let's also talk a little bit more about the things, in particular between Mars and Venus, that operate in a weakly magnetized paradigm. So the atmospheric escape processes at Mars the main ones are going to be photochemical escape, genes escape, and ion escape. Those are the three that we're going to focus on. That said, photochemical escape occurs, we'll talk about that in a moment. Photochemical escape occurs, that's the dominant loss mechanism at Mars today. At Venus, the gravitational well is too strong. So the escape of things like heavies, that's going to be oxygen, O2, and CO2, they can't escape from Venus because they're not in a neutral form. They're not going to get enough escape energy through photochemistry to do that. So the main way to remove the heavy elements in the Venusian atmosphere are going to be via ion escape. And that's really important when we think about how do we want to investigate the differences in escape processes at each planet. Okay, neutral escape, a quick reminder. Genes escape, those are going to be the light elements. Mike Chaffin is another one of our resident experts here on that. This is going to be the loss of particles from the tail of that speed distribution. Photochemical escape is basically a process of dissociative recombination. That's a neutral escape mechanism. Basically, you can break up O2 plus, and then when it breaks up, it gains an electron, and then you get these excited, there are different branching ratios if you want to talk about it later, but you get 2 higher energy oxygen atoms out of it. But again, this in particular is not happening at Venus. If it is, certainly not effectively. It might be 1/1000th of the time. So never say never, but it's not really a mechanism that takes place. So this is where ion escape comes in. The neutral atmosphere, oh, there it goes. The neutral atmosphere of Venus gets ionized by that incoming radiation. So you're going to have photoionization, charge exchange, and electron impact ionization. That upper atmosphere gets ionized, and once those particles are charged, they can start sensing electric and magnetic fields and get accelerated away from the planet. This is a diagram I did. There are lots of exciting ways that happens as well. If you want to talk more about it, I mean, this is like entire half the hall at AGU on the physics of how the escape happens. So things like, when you look at the electric field terms, pickup ions, bulk escape with those J cross B forces, and then you've got the electron pressure gradient terms, creating escape channels, and so usually in the form of ambipolar fields. There are lots of different ways. Once a heavy ion is charged, or once a heavy particle is charged, it can actually sense those fields and escape. And again, the big thing here is that at photochemistry, it won't escape in neutral form at Venus. So you need to have plasma instruments to be able to understand atmospheric loss at Venus. Okay, this is just an extra figure I was showing folks. And again, in the big picture of things, if we want to think about how much atmosphere has been lost over time, the reason we're doing this, when we want to think about the sources and sinks to help us constrain, things like outgassing, we want to think about our current escape rates. And one of the things we've done very well on MAVEN is take our current escape rates and then extrapolate back in time. And so we usually start here, and then you scale the EUV, you scale the solar storms that we know, things like coronal mass ejections, stream interaction regions, any kind of dynamic pressure increase. Those things are, these are like hurricanes eroding the coast, right? These solar transient events or storms are huge, have a huge impact on eroding an atmosphere. And so again, we take our escape rates, our EUV, and then we think about solar storms, and we go back in time, and we think about how can we start to constrain how much atmosphere has been lost. Assumptions we currently make, these are going to be the sun was much more active, and in all of these discussions, we're thinking post-bombardment and post-hydrodynamic. So that first 500 million years of the planet's formation was just so cataclysmic. I choose not to touch it and just pretend everything after that is going to be static and we can study. So this is an astrophysics seminar, so I wanted to mention that our Kepler folks fit in here into this talk as well and thinking about how to contribute there. When we think about, again, what the sun looked like at an earlier point in its lifetime, this is where observations of early sun-like stars really come in useful. And our Kepler colleagues have done an outstanding job of that. And so when we think about the sun, right, it used to be a faster rotator. And so as it's spinning down, it's losing that angular momentum and via the solar wind that's streaming off of it. And so that's why we have a quieter sun today. We think 4 billion years ago that we would have seen XUV and we would have seen solar winds hundreds of times higher. So again, that helps us scale using our models, the kinds of escape rates and the energy input into the system at Venus. And again, thinking about, we take today's escape rates, that's what we're after, and then that's how we start to scale them. So these sun-like star observations are really important. So if that's what you do and you find something exciting about EUV in particular, tell me. Okay, so one thing to mention here. One of the neat things about observing solar storms now is that they give us a glimpse in time of what a really active sun might have looked like. And so the solar cycle operates on this 11-year or 22-year, basically, this cycle. We're currently here in solar cycle 25, but here I've put the plasma observations. So if you're a Magellan person, I didn't ignore you, but they didn't have plasma instruments on, so it's not going to be in this chart. So these are the plasma observations at Mars and Venus since the 60s, basically solar cycle 20. And you can see who's observed in green here. Oh, I forgot my color bar. Red is Mars, green is Venus. So anything in green, some of these are flybys, Galileo, Cassini. We have Venera Messenger did a Venus flyby. But the big missions were PVO and VEX, and so they did get to observe some of that solar maximum. At Mars, we've had a smattering. This is current time. Mex and Maven are still healthy and doing very well. But so when we think about what extreme conditions may have looked like, we do have some observations, and many observations from PVO and VEX, but not with the resolution that Parker Solar Probe and some of our current assets have. Just a quick note on those, because I think it's useful to say, didn't we already see this? And the answer is no. So PVO had this equatorial orbit, right? So that meant periapsis is in the mid-latitudes and apoapsis is way out in the same equatorial plane. VEX was orthogonal. These are both 24-hour orbits. They're pretty big. And here, VEX was the periapsis was in the northern hemisphere, apoapsis in the southern hemisphere. So you can start to think about the region of space we were able to sample. VEX, I'll stick with the VEX results. Just a quick note. When they looked at the ions to say, okay, what's the ion escape? They could distinguish lights, so that's going to be hydrogen. And then they looked at heavies, and that's not hydrogen. And so that's sort of a big range when you think about atmospheric escape. And so while I'm not throwing VEX or PVO under the bus, they really laid the groundwork for our understanding of where to start with those escape rates, but they can't separate anything out. So we're not actually sure which elements are escaping and some of the physics behind how they're getting accelerated here. And you can see this channel. And this is relatively coarse resolution. For any of you electrostatic analyzer folks out there, I think VEX is like around 4-minute integration time, and PVO was like 7.5. So that's a long time to take 7 minutes at the speed of a spacecraft and smash it all together and say this is what was happening in one area. Just a little bit then about what are their ultimate results they found. So this is some, unfortunately, unpublished work from Tess McNulty, who actually used to be here. PVO and VEX era. When we look at the escape rates that we think were measured from oxygen versus O2, or even combined, the bottom line is the escape rate is here on the left. And on the right, that's the equivalent, what we call gel, or the global equivalent layer of water, if you covered the whole planet in water, because that's just a more meaningful number than 10 to the 25. And so even just the differences here, they're orders of magnitude. I mean, the bottom line is that we really haven't well constrained some of the escape rates on Venus. I think for some folks, it's pretty clear it's in this region. But even then, we've seen escape rates that have been way out of those bounds. The error bars are really large here. And so that's something we need to have better integration times and higher resolution instruments to be able to do this. Enter Parker Solar Probe. And all of us banging on about you have to turn your instruments on when you do these flybys. I'll go through this quickly, but the idea is to get practically inside of the corona to make sure that we can see, at their closest approach, they really want to get close to the sun, and to do that, they use Venus as a gravity assist to basically slingshot them around the sun. And they're doing 7 of these Venus gravity assists, or Venus flybys. So this is a top-down view, or a view from above the planet, of previous past and present plasma observations. So first I showed you that time series of where those Venus observations were. This is a top-down look if you just sampled them. Here you can see PVO here you can see PVO in red, and that's because it had that equatorial orbit. VEX had a slightly smaller sample size, and then we had a handful of flybys, Galileo, Cassini, and Messenger. So these are the 4 flybys I'm going to talk about today, and they went through some really interesting space. And in particular, 3 and 4 cut across the tail here, and that's where we're really excited about some of that atmospheric escape happening. This is another view, top down, so the same kind of view, but now we're just looking at the Parker Solar Probe Venus flybys. On the left, you're looking at the solar wind bulk flow, or velocity. And so this is going to be that proton velocity, we're a little bit north of 400 kilometers a second. And here you can see that interaction region. The sun is to the right. On the right, you can see the IMF strength. That's the magnetic field strength of the sun, so the interplanetary magnetic field. And so here you can see, again, that magnetic pileup as the solar wind and that interplanetary magnetic field from the sun encounter that obstacle and form that shock. And this is an MHD model from Yingxuan Ma. If you have issues with the jump conditions, I'll talk to you about that after. But I just like that this is a visual to show what that region looked like during these flybys. So where are we going to be? What are we going to be observing with respect to solar activity? These are the 7 Venus flybys. Here's the prediction of solar cycle 25. We started in that deep solar minimum of solar 24, so not a lot going on. But we're pretty excited about potentially seeing more activity in flybys 6 and 7. We'll be at the peak of solar cycle 25, so fingers crossed we see more intense activity then. I should quickly note, for those of you, we have many collaborators. So BepiColombo, which is looking at Mercury, and then Solar Orbiter, which is the European Space Agency's heliophysics mission, are also doing Venus gravity assists for their own science campaigns. Bepi has 2, Solar Orbiter has 7. I'll quickly show you. This is the XY plane, so looking down. This is the XZ plane, so this is the profile view. We're seeing a ton of Venus flybys happening, in the future or have already happened. So we're going from something like this to something like this now. So even though we don't have a current asset at Venus, one of the really exciting things is that we're going to have observations of Venus throughout the solar cycle 25. And this is something I'm really excited about because, again, if we see more solar activity in a range of solar conditions, we can take that, think about how they're constraining the physics of escape, and then start to think about how that creates sort of a bookend, right? Sort of a boundary condition for the sources and sinks in the Venusian atmosphere. Okay, on to the results. So the instruments the measurements we're going to be talking about today are fields and SWEAP. So fields, these are going to be electric and magnetic fields and waves. And so they've got a flux gate magnetometer, they've got a search coil magnetometer, and then they have an electric fields. And that's going to be measuring actually the electric potentials there. SWEAP is the solar wind, electrons, alphas, and protons investigation. That's a Faraday cup. And then it's called SPAN. And so the SPAN is an electrostatic analyzer. It measures ions and electrons. There's actually two, SPAN A and SPAN B. But in any event, we sort of consolidate all of their look directions. And so effectively, you get this electrostatic analyzer with a time of flight. That will give you the mass resolution I'm excited about. And then you've got this Faraday cup to help us understand the solar wind moments. The moments are things like the velocity, the temperature, the density. OK, so the first flyby, I'll start with the fact that Venus is really bright, incidentally. And so actually, once we got to the closest approach, the instruments thought they were looking at the sun, not a planet, and they all turned off. And so lessons learned. We were the very first to do this, and that didn't really help my campaign of like, you won't even know, it'll be really easy. But then we had to do quite a bit of work for the second flyby, which did work. So what you'll see at the closest approach, we'll stop taking observations. But nonetheless, the observations up until that point are really cool. If you're a shock person, and one of the neat things here is that this is right along the quasi-parallel edge of the shock. That tells you a lot about some of the energy input. So if you're into waves and instabilities, the first and second flyby are very cool for that. Here's that second flyby, and we made it all the way through. Again, this is a zoomed out version of the MHD model. Let me go back a minute. These are this is the INF streamlines, and again, we're looking at the same thing. This is the solar wind velocity, and this is effectively that magnetic field from the sun piling up around the planet. So you can just start to see the general geometry, and this is a top-down view again. Here is that second flyby, and so this is where you're going to, again, same thing, quasi-parallel edge. So really interesting geometry here. This is the way I like to show. I'm going to start with these. Yeah, I think I'm OK so far. So when we look at the first flyby on the top yellow line, what you're seeing, I decided to pick just a few points of interest. Is this the pointer?
Yeah. Orange is power.
Orange is power.
Red is point.
Red is point. Perfect. Thank you very much. OK, so here, this is the first flyby. And the points of interest I thought were neat. When we first got the magnetic fields down, those are admittedly much easier data products to work with if you're a plasma person. It's 3 vectors, which is great. And so we didn't actually have the plasma data yet. And so we didn't know if it was heated or not. So we actually thought, we went through, we see, let's go way over here now. We see some really interesting wave activity. And you can see at points 1 and 2, these rotations and compressions in the solar wind. And that's going to be indicative of the foreshock. And so you're getting these backstreaming particles coming in and really, really like sort of infusing the shock with a lot of energy here. At this third point, you're starting to see more activity. We actually thought the second point here was the bow shock crossing when we first looked at the data. However, that's actually not the case. The shock crossing is much closer in than we thought it would be. And so here, we see that shock crossing. You see this huge jump in the magnetic field here. That's what happens with the bow shock. It's when everything kind of piles up, and then you cross it, and you just get this huge jump in the plasma and the fields. And then you enter into this whole shock region. And then right here, I'll zoom in for everybody, we actually got into the magnetosheath. OK, here's the second flyby. Some interesting, here you can see we made it all the way through. And this is where we're skirting inside and out of the shock as we pass by it. And then again, there's some interesting points there. You can actually see the outbound shock crossing, which is useful because it's much closer to the terminator. Here are both just lined up. I thought this was sort of neat to look at. You can actually start to see some of the differences in wave activity, even just between on this kind of a scale. So you're looking at even just a couple of RV or planetary radii apart. The difference in that heating and that wave activity in that foreshock region is really quite large. OK, so if we were just to look at the data set, you're looking at altitude, density, the proton flux, the alpha flux, the electron flux, the magnetic fields, the wavelet, that's the BX component of the wavelet, and then the electric field measurements. And here you can see that foreshock region again. You're seeing a much quieter solar wind there with a little bit of structure, but then you can start to see, which side is it on? think that side. There we go. So you can start to see some of the wave activity really, really pick up there. I'm going to zoom in a little farther. That's the first shock. Oh, one thing to note for this first flyby, because again, I was already pushing the envelope a little by turning on, the ions we measured were only 500 eV to 2 keV. If you're not an ion person, it's fine. It's not great at all. If you're an ion person, you're looking for like 0.1 eV to call it 25 keV or something like that, which happens to be what Maven's energy sweep table is. So, okay, when we zoom in even farther on this first one, here, this is the solar wind. You can see once we hit it, here you get this heated, shocked plasma. All of a sudden, you get this jump in the magnetic field, and you're seeing much more wave activity. One of the neat things is we're going in and out of the solar wind. You can actually see it. As that black line on top, green is the sheath, and black is solar wind here. We hit the shock, and all of a sudden we come back out. It's cold again. And you can see we're even going in and out of it here. You can see, if you really zoom in, and I don't have time today, but it's really fun to go down to like the sub-second level. You can start to see we're going in and out of that shock, and just the wave activity here is just crazy pants. You're seeing a lot of heating and a lot of really exciting activity. And a couple papers have been published just on this region alone. VGA2. I'm going to condense it a little bit more. Here you're looking at altitude, the electron flux, the magnetic fields, and that BX wavelet. Oh, and if you're looking at this line, that's just the reaction wheel. It's an artifact that we're just too lazy to remove, so ignore that piece. It's not science or anything. Here, we come in, we hit the shock, and then you can see again, we kind of come back out of it. And then you can see that heated plasma again, and there we are. You can see a lot of activity. It's also interesting because it's not really symmetrical. Even though while you're going through, you're seeing really different sides of, as you get closer and closer to the terminator region of the planet, you're seeing a different kind of heating. Okay, so this is the third Venus flyby, and this one I'll spend a tiny bit more time on. Actually, I'm going to pause a minute. I sort of like to do discussions. Does anybody have a question on the first two flybys for now? Go ahead.
Why can't you see the solar wind and the proton data? So I'm used to seeing a beam at like 1 kiloelectron volt that's directed anti-sunward.
That's so. Well, for one, the pointing was not great, unfortunately. In particular, for the first flyby here, you can really see it. I think in the it's pretty smeared because the range we were looking at in the first flyby was, I think we said, 500 to 2 keV. But even then, it's the pointing just wasn't very good. And that was just a function of how you slingshot yourself around the planet.
So you're not seeing the solar wind because the instrument field of view is excluding.
Yes. And so the question for anybody online as well was, why don't you see that 1 keV solar wind population? And so the idea is that for SPAN, the electrostatic analyzer, it was not pointed in a way that you would see that incoming, you'd see that sort of RAM flow.
So you know you're in the shock because you're seeing all of these backscattered.
Yes, exactly. You see the heating, and then often we rely heavily here on the magnetic fields, right? You're seeing a lot of that wave activity. So here is the kind of place where you would start to really look for the wave activity to tell you more or less what the heating is when the plasma is not able to do so as well. For the second flyby, the pointing was a little better, not terrific, but one of the things we are able to do is use the Faraday cup to get some of the moments. The Faraday cup had much better pointing, but then obviously it's just a cup. And I shouldn't say just a cup. It's an instrument that doesn't have the kind of resolution between some of it doesn't have the kind of energy and mass resolution we'd be looking for. Any other questions on the first? We can do it after too, but I always like for just a moment. Was there a question over here or no? Okay, we'll keep going. Okay, so for the third Venus gravity assist, one of the things I thought was really, really neat was that we had this cutting across the tail, and this is where we can start to think about the escape. And so here on the time, you can see we're starting down here. This is a top-down view. Same thing again. You're looking at the proton, the speed of the solar wind, and then you're looking at the magnetic field strength. And we're cutting across the planet here. And so one of the neat things when we cut across, this is where we can actually start to think about what those heavy ions might look like. The fourth one, same thing. So these are very similar geometries. And again, that's to actually get the spacecraft as close to the sun as possible. Okay, so this was back in 2020 in July. So what you're looking at, look at on this side, altitude. You're looking at altitude, the protons only, the electrons, that magnetic field, and again in VSO coordinates. And then you're looking at that BX wavelet. And again, you can see the reaction wheel in that wavelet. Just ignore that. So the things I'm circling here, here's the shock I've labeled in each. One of the neat things, oops, here we go. We thought this was a foreshock region, but these are pickup protons, believe it or not. One of my colleagues, Ali Ramadi, was actually able to backtrace their energy. And so this is an interesting area where, trying to understand the source of hydrogen is a really important piece of the puzzle in terms of saying, did it come from the planet or did it come from the solar wind? It's hard sometimes when you have the same species, and you don't actually know where it came from because they're a couple of different sources. So this is actually planetary. This is actually planetary hydrogen that was picked up and accelerated. One of the neat things here is this rotation in the magnetic field. And it's not just a rotation. I've been working with Taifan and a couple of others, and understanding if that might be, in fact, magnetic reconnection. One of the neat things is almost in that same exact area, we can, for the first time, distinguish this back anode, I just pointed the pointing direction, the O2+, the O+, and the CO2+, as well as those back anode heavies. So here, you can start to see, point to Mike's question, these are actually higher. This is a higher energy population than you would think the solar wind would be. And then here, for the first time, we're seeing in the same place as this really interesting rotation in the magnetic field, we're seeing these heavy ions. And often you see that with magnetic reconnection because magnetic fields reconnect and then accelerate the ions. So first results, these are not published anywhere, but the data is not available anyway. So, this is a first and exciting look. These are the first ever observations of the different species at Venus that are resolved. This is from SPAN. Here you can start to see, this is the energy over charge, and then you're looking at the, well, I think I probably hit that. There we go, and then there's the time of flight. The long and the short of it is here, we have our water group, right? Here you can see and that's in purple, and then in green, that's where you're seeing those the major species that escape. That's your O+, your O2+, CO2+ was a little harder to see here, but here are the main constituents and the energies that we saw them at. You'll notice that O2+ was going the fastest, which I thought was really interesting. I would have expected O+ to be the dominant ion and then it to be going the fastest. That said, that's because I'm used to seeing that at Mars in the same region. Here, we're seeing O2+ is being accelerated. So that also tells us likely you might be able to infer there might just be more O2+ in the system in general. And so this is one of the really cool results that we're trying to get them to calibrate the data, get the data out publicly so we can get this into Science or Nature. Here we're seeing something similar. So this is VGA4. You're looking at the altitude, the protons, the electrons, the magnetic fields, then that BX wavelet. Here again, you're seeing some really interesting activity. And you can see here's that heated plasma in the electrons. You can see some of the protons here. The field of view was not terrific, but it is what it is. And then here you can start to see that rotation in the magnetic field. Same region here, you can sort of take, with your mind's eye, you can sort of line everything up and zoom in even further, but because the resolution is not terrific here, it starts to just become like a giant red block. You can start to see, again, those heavies, those protons, I should be doing this. You can start to see these heavies, and then you can start to see these protons. That's the thing we're really, really excited about. Here, the breakdown is something we're not, they wouldn't let me show. It's in such a raw form yet. We're not ready to assign energies yet. These are tricky, time of flight, it's a tricky beast for those of you that do this kind of thing. So we're still separating that out, but really excited because we certainly saw the heavies and they are separable. And so that's one of the really, really neat things. Okay, future missions to Venus. This is where you can write your local representative and tell them how it's criminal that we have no plasma instruments on any of the upcoming missions. So we have Veritas. Veritas is going to be looking at, well, effectively geological evidence for volcanism. And that's a very important topic. Again, circling all the way back, getting those present-day escape rates tells us about what's leaving the atmosphere, but we need to understand how it's being replenished in the first place, because Mars and Venus are just not the same. We're not worried about where the water went at this, well, it's one of the things we're interested in, but we're not worried about where the atmosphere went because it's got 90 bars of atmosphere. So where is it getting all that atmosphere? And then Da Vinci is going to be looking at a lot of those isotopes as it drops down to the surface, and so that's a probe. So really exciting missions, and they're going to be looking at, again, some of the same things we're fundamentally interested in, aspects of the atmosphere and ultimately the interior of the planet. You know, how do these atmospheres form, and what's the evolution of the planet? But there's no plasma. You know, these are easy, cheap things to build, so if you know someone, you should tell them they ought to add something. Envision is in the same camp. That's the European Space Agency's upcoming mission. And so that's going to be a little bit more like Veritas, right? And so it's going to be using radar to be, looking basically at the planet and understanding what the surface can tell us about its history. Okay, so I just wanted to finish up with a few, I've got a few more slides here, but if you're a Balshock person, I wanted to briefly point out one of the neat things that the Bertucci paper back in 2011, it was a space science review on Mars, Venus, and Titan. It tried to do a fit of the Balshock, and so I thought we ought to be doing the same thing. But the Balshock parameters are really, I don't want to say they're all over the place, but even this last point here for VGA4, we actually saw pretty far out, and I was sort of surprised by that. So I think we're trying to understand what the solar wind, like why we're seeing this distribution. Some of them are right in line, but some of them are not. Effectively, the bottom line is we're seeing a narrower angle for that Balshock. The Balshock is an important indicator for basically the pressure balance in a system, which is again a big picture. Here's the solar wind. It comes in and is balanced with things like the thermal pressure from the atmosphere, the magnetic pressure, et cetera, et cetera. And so that pressure term balance effectively is what decides where the Balshock is. And so when the Balshock's moving, Balshock fits are important to tell us, again, about those pressure balances. I should also highlight some of the first results that we saw in a special issue from Parker Solar Probe. Some of you are hopefully familiar with these. So Katie Goodrich in 2021 did a really, really neat paper on some instabilities. Trevor Bowen did some turbulence work here with the Parker Solar Probe data. Mark Palupa did a fabulous paper. We did not see lightning. I will repeat, we did not see lightning. Sometimes, I won't name anybody, but sometimes people publish papers saying we saw lightning, and it's really hard. First of all, it's really hard to determine if we actually did. And second, this is where you really have to know the instrument effects to see if, you would be seeing that kind of, if you'd be able to see if you're magnetically connected or that Schumann resonance is present, et cetera, et cetera. Mark took a look and solved it. We did not see on the first two any lightning. So this is not to say we won't, but. And then finally, David Malsapina did a really nice double layer paper. And so this is, for both Katie, so the Goodrich and the Malsapina, both of them, this is the first time we've seen some of these kinetic effects at Venus. They've certainly been observed at Earth before, but it's really nice to take what we know about Earth and then think about how it applies to Venus. So, okay, I will wrap it up. I think this was 50 minutes total, so I think I got the timing right, hopefully. The conclusions are, so the sources and sinks in the Venusian atmosphere are fundamental to understanding terrestrial planets in our solar system and beyond. I should note on this point that if I had a nickel for every time as modelers, and I am one, we take Venus and inject it into a model to understand exoplanets, that works, and that's helpful for trying to understand, would JWST, would Webb see it? With certain kinds of telescopes, could you resolve spectral features in the atmosphere? Those are all really exciting, but it's really tricky to be able to do that when we don't fully understand the sources and sinks in the Venusian atmosphere at present. So the heavy ions, hopefully one of the big takeaways today is that heavy ions are the way we understand loss in the Venusian atmosphere. Photochemistry doesn't occur efficiently at Venus. So we need those plasma instruments to detect if the atmosphere and how the atmosphere is escaping. Shocks, waves, and reflected particles, meaning the force shock in particular, are really important in understanding that interaction region. Often we think the kinetic scale physics are exactly that, they're small, but they actually have a huge impact on the larger scale system. They're a huge and important source of heating, and that heating is ultimately how we energize the charged particles and then you can escape the system. Finally, we've done a lot of firsts. So again, if you get a chance and you're interested, please read some of those papers. I should also note I didn't get to this slide, and I can see Nick's in our in our camp here, so I didn't get to the WHISPER images, but there's some other really interesting Parker Solar Probe studies that have been done. So WHISPER is one of the really neat instruments that's been able to look at the cloud deck at Venus, as has Akatsuki, and those have been able to also do some really fantastic imaging of the dust and some of the surrounding dust region at Solar Probe. That's been something we just didn't expect to see in general, is the dust, the dust, effectively this whole ring in an area that we hadn't actually observed it before. So if you get a chance, please check out some of their information as well. And then finally, the BepiColombo, the Solar Orbiter, and the Parker Solar Probe teams work pretty closely and have some really exciting working groups. If you're interested, let me know. This is open to people who are excited and we're on work on the data. And we're trying to coordinate and collaborate all of these Venus observations so we have a big picture understanding during the entire solar cycle 25. That's it. Thank you.
Wonderful. Thanks so much. So we'll open it up to questions, and I was reminded to offer this to students first. If anyone has questions, great.
Thank you. Hi. I was just wondering how often magnetic reconnection events happen. This might be a naive question because I don't understand magnetism. But the date on the two Flyby 3 and Flyby 4 were like a year off, and both of them had magnetic reconnection, or what you were interpreting as potentially magnetic reconnection events of like that flip. Do they happen that often? Is this? Yeah,
so the question was, how often does magnetic reconnection happen, in particular in the Venusian tail, is really the piece. Let me see, I don't think I put it on my, let's see, let me go all the way back here. And it's not in my backup, damn. Of course it's the time I forget. So, okay, so in theory, magnetic reconnection can be happening all the time. It's interesting, so Venus Express did the first, some of the first definitive observations of magnetic reconnection. I should be clear, we're not positive. So there are ways you can look at magnetic reconnection that are pretty quantitative. You use eigenvalues, and you can actually effectively see the magnetic field rotating and reconnecting and all of that. So to answer your question directly, it can be happening all the time. How often do we observe it? It's a little hard. I mean, right now, so Venus Express, they had a decent number of observations. So there's some really interesting papers on flux ropes and tubes. And so flux ropes they're almost like these magnetic bubbles that form. And so there are a number of studies there. So I think some folks at LASP, I know Takuya Hara at Berkeley. I know I'm forgetting other folks. So flux ropes have been observed pretty frequently when you actually fly through the region that's sort of reconnected itself. So the observational piece, I guess I don't have a statistic for how often you would see it, but how often does reconnection happen? I mean, I would say at least daily, if not. I mean, Dave, do you have probably?
It would be happening all the time.
A lot. This is a super helpful answer, but I would say, I mean, if you could, for example, hypothetically, if you had a CubeSat, where you had like 15 different orbits, and you could get into the tail, I would expect to see it at least, a couple times a week, if not multiple times a day. And that said, I should be clear, especially because I'm sure my magnetic field colleagues will just check for this part of the talk. We're not positive in our case that this was reconnection. On Flyby 3, it's looking strong that it was, but one of the really helpful pieces there is to look at the plasma simultaneously. That can tell you these sort of jets form when you get into what we call an X line. And we're still trying to work with the particle data to see if we really think that's the case. So, because sometimes the geometry of reconnection is not a white. Can I draw on this? No, I won't. It's fine.
Go for it.
One of the things is. Yes, well, I'll just do this. So like often, if you have like a perfect bubble, where you cross through, you don't always cross through at like the perfect point. You might just like skim the edge or go right down the center. Sometimes, the way you fly through it isn't perfect, and so it can be a little tricky with just the magnetic field rotation to understand what you're seeing. And they're also not perfect circles. They're often these like weird blobs and tubes that are all over the place, so. Okay.
So I'm just going to jump in before going to you. Just
Please.
a naive question. So if Venus is non-magnetized, where are you getting the reconnection from? It's
yes, and I
in
can't
the solar
believe I
wind
don't have
and-
my figure here. Let's go back to this one. This is a simplistic view, but what happens is it's not actually perfectly asymmetric in the tail. Like if this is the planet and I'm the solar wind, it's like you're hugging it. It kind of comes up, the solar wind wraps around it like this, and then forms a tail in the back and sort of stretches around it. But that said, that's even then, the solar wind, those interplanetary magnetic fields induce the tail, and they're moving around too. So you can almost think about like a jump rope or something hooked around a column, and you're doing this. And there are lots of them doing that. And so there are actually lots of fields in the tail that are forming that have the ability, because they're going opposite directions, and that's how you would actually form it. It's this induced tail. Does that make sense? Okay.
Thank you for the interesting talk. I have a question to confirm how the amount of other species are measured, especially in a third crossing event. I think there are some 12-volt assumption or something.
I missed the end of your question.
Yeah.
No, I'm sorry. Just didn't.
How the amount of other species are measured? If we apply 12-volt correction, well, what's that?
Oh, that's right. So, spacecraft potential and understanding, looking at the actual how you scale that to the velocity. So this would say on average for all species. It's a little tricky because these are occurring in different places. And so when you resolve them, when we're actually looking at those integration times, the way it was applied, are you asking about how it was applied or how it would affect all of these? You would be looking at really, you'd be certainly looking, we think, at a colder water group species. So that would be pretty cold. And then all of these have already been corrected though. But the average, because hydrogen is just the highest flux, on average, it's around 24 kilometers per second. Does that answer? I feel like that doesn't answer your question.
Okay, yeah.
It does?
And, yeah, and can I ask another question?
Please.
So the Parker Solar Probe will observe the sun, Venus, in solar maximum. And
Yes.
what are there any expectation? What's going on if solar activity is higher? Because I'm interested in a superactive phase in the younger sun.
Yes, so the question was, what can we expect for high solar activity with the Flybys? If we see a really big storm, I'm opening champagne. That would be fantastic.
Yeah.
That said, realistically, do storms happen all the time that are directed towards Venus? I think I might even have this as a backup slide. God, there it is. This one kills me. So Maven did a whole special issue on the September 2017 event. There, it's already playing. Look at that. There's Venus by itself. Well, you see Venus, and guess who was not there? Us. Nothing. Nothing to be seen at all, even though Mars was really perfectly aligned. We saw this throughout the inner solar system, and actually even farther out. That said, there was nothing at Venus to see this. This is the kind of event we would absolutely love to see. The likelihood is going to be much higher. Let me go back to let's go to a solar cycle plot like this. So for Flybys 6 and 7, and 7 as a reminder, it's going to cut across the tail, the likelihood will be stronger. I should also point out stream interaction regions. We didn't really talk about this. That's when the fast solar wind and the slow solar wind sort of meet. It's almost like getting rear-ended, but not entirely. And either way, so you get this like compression region, and that's always happening at the sun. So that would be a reasonably, I'm actually surprised we haven't really seen that yet, unfortunately. A stream interaction region would be an incredible thing to observe just because it's an increase in that dynamic pressure. But a CME, again, bubbles for everybody if that happens. And it's more likely, but a CME frequency, Ed's not here and neither is Phil, but if anybody knows, just shout it out. But it's going to be closer to like maybe 1 or 2 a month. So if it happens right when we're there, great, but I wouldn't count on it.
Thank you.
Yeah.
Hi, great talk. I was thinking about how most rocky exoplanets that are amenable to JWST transmission spectroscopy are going to be Venus analogs rather than Earth analogs. And I was wondering what these sort of in situ measurements that we can place from Venus might do to help us to better understand atmospheric loss of Venus analogs as we're trying to get better spectra with JWST.
Yeah. No, I completely agree. So I think this is where having more ultraviolet instrumentation would be enormously helpful. I'd love to say ions solve all the problems in the world, but I can admit that that's not quite the case here. So really what we need are, again, things like the camera bands. We need much better ultraviolet measurements with higher resolution to be able to do that. And so that is something that some of the upcoming missions, I'm not as familiar with their UV instrumentation, but we'll get some better, but that's the kind of thing where, right, more infrared, more ultraviolet, and those are the things that would be really, really useful. Vicky Meadows has done some really nice papers on looking at some of the transmission spectrum from, in theory, Mars, Earth, and Venus, and then saying how would you, what would these look like, given the resolution of JWST and whatnot. But UV and IR data would be enormously helpful. Obviously, IR for JWST. Would be really, really helpful. And also just understanding more of the, I'm going to call them seasonal effects, and understanding why we're seeing some of the variation that we are. So with Venus Express, we saw a lot of variability in some of those and some of that spectra. And so I think that's something that we just need to get to the bottom of. And this is not my area of expertise, but certainly returning missions should include that kind of instrumentation.
Thank you.
Yeah.
How well do you understand the ionization balance in the outer atmosphere?
Do you mean the processes like photoionization?
Yeah,
and
relative
right.
importance of the processes and things like that.
Yeah, so I mean, you've got photoionization, electron impact ionization, and then you're going to have like charge exchange. And so photoionization, just because of the radial distance from the sun being closer in, that's really going to toast everything on the day side. So you're going to get, that's going to be the dominant mechanism for ionizing that corona. It's not as extended as Mars, naturally, because of the scale height. Venus is a more massive planet, so it tucks everything in just a little closer. And so then that corona is not quite as extended. But photoionization will be the main and dominant source. That said, there's some really interesting studies with VEX, and that we're trying to look with the Flybys 3 and 4 on these sort of electron holes and then areas of intense electron densities in the Venusian tail that I think could be responsible for a lot of the electron impact ionization. Because electron impact ionization is really temperature dependent, and we often forget that. That TE term is often applied a little loosely. And so that's where we could think harder about getting a better handle on those temperatures to see what those ionization rates are in that particular term.
Hi, Shannon, thanks. I have a question triggered by the fact that this slide is up here now. So you showed us individual flybys of Venus and the analysis that's being done with those individual flybys, and I'm starting to think about how all of that's going to be integrated together to get back to your big picture goal of understanding ion escape from Venus over time. And is the idea, are you starting to see trends or patterns from the flybys that you have so far? Is the idea to compare all these flybys to each other, or is the idea additionally or instead to compare these flybys to other data sets from PVO or Venus Express with the higher resolution observations here, put them in context with the other spacecraft?
I mean, I wanted to say yes and then end it, but I think it's an assortment of things. So it really depends on what sort of slicing and dicing what you want to look for. So on the one hand, I think we'll start with the kinetics and the shock physics. I think that that's a little easier to compare across the solar cycle because that's where you can look at the moments themselves and you can see the shock to fit. So that's one set of comparisons we'd like to do, is say, what PVO and VEX data have shown us this with the shock fit. And now we've got all of these other samples. Let's see the fits and try and understand where the variability is. When it comes to ion escape specifically, certainly we have to put it in context of VEX and PVO. That said, and I've got a chart here, at the very end, I would like to reconstruct this chart. So this is the historical instrument coverage. Oh, and this right here's where you can start to see the resolution. You know, PVO, the OPA, really missed a lot of the energy. So it was 50 eV to 8 keV. So you're not going to see a lot of the heavier species. That's like the solar wind. And you can't see the low energy ion population. As a note or reminder, at Mars and with MAVEN data and MEX data, we know the majority of escape is like under 25 EV. That's the majority of the ion escape at Mars. At Venus, if you start at 50, jury's out. VEX, the energy resolution was better, and here you can start to see, okay, you can see it here on the chart. The top row is the energy range, and then and I put in red boxes the ones that I showed comparisons to, and the bottom, that's going to be electrons. So the top row is really the one you want to look at over time, and you can start to see the range. But VEX couldn't distinguish them and still had that huge resolution. So what I'd like to do is try and reprocess, in particular, the VEX and PVO data, like at sort of certain points in the solar cycle, similar. And then what you could do is take the data points, and I do think it has to be from all of the missions, because I'd love to say our 7 flybys count, but really only 3 go through the tail. So that's 3 data points now, or 3, I should say, flybys. And so you need to take all of those flyby campaigns where you see data in the tail, and then compare it in similar points in the, not just solar cycle, but say, what were the solar wind conditions during that orbit, and compare them to then the corresponding times that VEX and PVO saw similar type conditions. And that's where I would do the comparison. But I'm open to suggestions. So this is an exciting data set. While the sample size is limited, it's certainly better than 0 data. So.
Thanks.
You posed the question at the beginning, where does Venus's atmosphere come from? I'm not sure that you answered that question, but I would have thought that since Venus lives in a fiercer environment closer to the sun, has less magnetic field, I would have predicted it would have less atmosphere than the Earth. What's wrong?
Same. Ugh. I would say we should all point to Bruce or any of the geologists in the room and say this is a you problem. So that's my answer. But I mean, I think that the obvious one is, okay, so at Venus, the escape rate in ions is an order of magnitude higher than the ion escape rate at Mars. And the net escape rates, if you count everything leaving the system, is probably about equal. That said, 90 bars, 6 millibars, 90, so this is where unequivocally you know that outgassing or the source region has got to be a beast. And this is where I try and coordinate with our fellow geologists and say we've got to understand the interior, and we have to understand outgassing and volcanism better to understand where it came from. And to your question earlier about exoplanets, this is key, because we just sort of slap a Venus in the system and say it's fine, but we don't understand those source regions. If we don't understand that, you could have a planet that's habitable or not. I mean, to me, the source region could very well be one of the biggest keys of habitability that, I don't want to say gets overlooked, but we need to look harder at and think about, that balance. So, no, I don't know. Bruce has the answers.
Thank you.
Yeah.
Great. We are at time. Maybe
So the answer
you have
is
answers.
that
Oh, boy.
the greenhouse effect that Venus decomposes carbonate rock, the amount of carbon dioxide on the Earth and Venus is about the same, but on Earth it's formed by biological organisms into rocks that are subducted under the ocean crust.
There is, and that's absolutely true. There's also been a recent debate I've heard, and I'm not really well informed on, that the redox rate is questionable now, and that the oxygen that we're observing doesn't match what that rate should be. So I think that there's still a lot of holes in our knowledge on what the redox situation is and what that surface, here you can see that those surface processes are there. So yes, the greenhouse is a major, major player, but I don't think it solves all of my understanding is it doesn't answer all the questions about how that much atmosphere got there. My understanding. But
Perfect. We'll end with open questions. Let's thank Shannon again.
yeah. Let's switch everything off.
Hi, can I ask you a couple questions?
Yeah, and if I butchered the hydrogen discussion,
No, it wasn't where you were going, so it's
no,
okay.
I was like, it's just a totally different talk, and I was like,
Yeah.
let's do that.
I can give you some.